Okay, this is going to be another example of a molecule that's covalently bonded and has to use hybridization to create the bonds that are expected in the molecule, and looking at the energy level diagram and how the atom goes through its change. So what we have here is carbon with a couple hydrogens and one double bonded oxygen. That oxygen would have 6 other electrons associated with it. So carbon sharing one here, and then 1 and 1 with this oxygen, and then this oxygen is providing the rest of the electrons there. So carbon is the central atom. It's the one that we want to consider the energy level diagram for. We have a 1s shell that's full. We have a 2s shell that, before any sort of hybridization or anything happens here, would be full. And then we have our 2p shells, 1, 2, 3, with 1 electron in each of those. We can see that this carbon wants to form 4 bonds. On top of that, we can see that 1, 2, and 3 of them are single bonds, and then we have this secondary bond over here that's different, that's a double bond. So we need to promote an electron, and we need to change our orbital shape so that all the single bonds appear the same. So first of all, let's imagine the first step in our hybridization process, promoting an electron, and then let's consider the changing shape. So when we do that, our 1s electrons are obviously left alone. But what's going to happen here, and this is a little tricky, we have to count our number of bonds that actually represent single bonds, because those are all the bonds that have to remain the same. So this is a single bond, this is a single bond, and this is a single bond. So what we're going to imagine then is that we're going to take 3 of our orbitals and we're going to hybridize those so that they're the exact same. So this hybridization would be an Sp2 hybridization. 1, 2, 3 orbitals there. 1 electron in each orbital. And then we have a p orbital that's still sitting up here. This p orbital is going to be associated with the second bond and the double bond. So that p orbital is left alone, and that's going to form a secondary kind of bond that is going to represent what's going on with this double bond. So first of all, imagine our hydrogens here. One hydrogen could be here, bonding here, and the other hydrogen could be here, bonding here. And then our oxygen is forming its first single bond by bonding here. Our oxygen is also bonding up here to form our pi bond, or the second bond in our double bond. The Sp2 hybridization, remember I said in the previous video that Sp3 looks like a tetrahedral. The Sp2 we call Trigonal Planar, which means just in one plane, this isn't three-dimensional at all, it makes a triangle. Okay? Now, if we have our carbon then, with its new Sp2 orbits going in all the directions, we can imagine putting a hydrogen up on one, and a hydrogen over on the other, and then we can imagine our oxygen, which will be sharing an electron directly here, and that's the first bond and the single bond. But then there's a secondary thing going on where it's forming its double bond. These bonds, where we have overlapping orbitals, they're the first bond in a bond, first single bond. We call these guys sigma bonds. They get this funny symbol, sigma, and they represent a direct sharing of electrons. To form double or triple bonds, we need to use a secondary type of bond called a pi bond. Because there's no more space available directly in between the two atoms, they need to find another way to share these secondary electrons. The way they're going to do that is they're going to share them in another dimension. So if this entire molecule is existent in the plane, then this is going to be a little hard to imagine. But we can imagine an orbital, a pi orbital, that's going in and out of the page. And similarly, oxygen would have the same pi orbital that's going in and out of the page. By doing that, they can create a secondary space that's in another dimension from all the other bonds that they're forming that allows for space for the double bond to form. Again, this would be like in and out of the actual surface here. We're trying to draw something that's three-dimensional in 2 dimensions here. And this secondary bond is called a pi bond. So hydrogen would go on each one of these sp2s, oxygen would get one of the sp2s, and then for the formation of its double bond, the pi bond, which we keep separate from the hybridization, we would draw orbitals that represent a pi orbital that's in and out of the page. For a double bond, we'd have this. For a triple bond, we'd have to have another dimension where the electrons could exist maybe forwards or backwards or side to side, where the rest of the atom is bonded accordingly. So that's how we can take our energy level diagram, our Lewis structure, and use it to really understand the shape of this molecule by recognizing the type of hybridization, in this case sp2. So remember I said sp3 is this tetrahedral, sp2 is what they call trigonal planar, where essentially it forms a triangle in the plane. And then how we handle double bonds, or the second bond on the double bond, which gets the special name, the pi bond, that's represented by p orbitals that would be existent in and out of the plane. I'm going to keep going with more examples of atoms and how to figure out what their shape is and how to do their hybridization.